So, as I said, I saw the computer freeze and stop moving, stop recording again. I really don't know why it does that. But as I was saying, this is the population correlation coefficient, rho. And we were saying that we're assuming the null hypothesis is true. We're assuming that in the population, there's no correlation whatsoever. And then our null hypothesis is that, oops, wrong way, it's different from zero. Just meaning that if we reject the null hypothesis, we reject that the population has no correlation, meaning that there is some correlation. It's different from zero. So we may use our linear regression equation to predict values, okay? So if we reject the null, our correlation coefficient is significant, and we could use the regression equation. If we do not reject the null hypothesis, then we cannot use the linear regression equation to predict our values. Okay, so that's what these are saying. So let's go ahead and do an example. Let's see, we are going to test at the alpha is 0.05. A lot of these linear regression tests are tested at the 5% level of significance. And we're just going to use the linear regression t-test. So we're going back to that first example with the 11 statistics students, and if you know their third exam score, can you predict their final exam score? So if I go over to stat, go over to tests, scroll up, it's faster, it's option F, linear regression t-test, and now mine says list 3 and list 4 because that was the last problem I did. I need to change it to list 1 and list 2, and then beta and rho, don't worry about what beta is. We want rho is not equal to, because in our null hypothesis, it's always rho is equal to 0. Our alternative hypothesis is rho is not equal to 0. That's always going to be the case for these problems. So now, store my regression equation. Let me go through how to get y1 into there. You hit your vars button. You go over to y-vars, you click right, you go to the first option, function, y1, and then you go down to calculate. Now let's talk about these numbers. T is equal to 2.657, P is equal to 0.0261, and degrees of freedom is 9. Now, for a linear regression t-test, degrees of freedom is n minus 2. We had, in this case, 11 sample points. 11 minus 2 is equal to 9. So that's where that's coming from. This is the p-value. Okay, this is the same p-value that we were calculating in the previous, or in chapter 9 for hypothesis testing. This right here is the test statistic, okay? There is a formula in the book for the test statistic. I don't necessarily remember what it is. It's something like r times the square root. I think it's degrees of freedom divided by 1 minus r squared. I think that's the formula. And if you were to plug in your r, get your degrees of freedom, you could calculate the test statistic. And since this is a t-test, you would be using t-CDF on your calculator. Lower bound would be the negative version of this. Upper bound would be the positive version of this. Degrees of freedom would be 9. And you should get this p-value. Okay, you could use t-CDF. However, we're not going to worry about the test statistic. We're just going to focus on the p-value. So if we're testing this at a level of significance, alpha is equal to 0.05, Well, our alpha value is greater than our p-value. 0.05 is greater than our 0.0261. Oh, I think I wrote it in the opposite way in the previous chapter. So here, let me do that. P-value is less than alpha. 0.0261 is less than 0.05. When our p-value was less than our alpha, think about what we did. What was our decision? It was reject our null hypothesis. Reject H naught. So what this is saying is, since we rejected the null hypothesis, that means there is a correlation between the third exam and the final exam. And we can use the equation. Let me write the equation up here. A plus x negative 173.51. B is equal to 4.827. We can use that equation to predict y values, okay? So this would lead into section 12.5 prediction. So I'm going to do it right now, 12.5. Prediction. If your regression equation is statistically significant, you could use it to predict values within the range of your smallest x value, your smallest y value, your smallest x value and your largest x value. Okay? This is called interpolation. When you use x values within the range of your data. So since we could use this equation, what it may ask us is, if my exam 3 score is, this is out of 80, let's see, what number is not on there? Is a 72, what will my final exam score be? So that's the kind of questions 12.5 would ask you. And it's called interpolation. Now, if you look at your data, your lowest exam score on your third exam was 65. Your highest exam score was 75. So this equation is only good within the range of 65 to 75 for your x values. That's what interpolation is. When you go outside of your x value range, it's called extrapolation, and you rarely ever want to do that. You rarely ever want to go beyond what your data range is. If you want to go beyond, there's other methods you'd have to do, and we're not going to go through that. Okay? Now, if the equation is not statistically significant, you can't do predictions. Okay? So in the next example, we're going to see, we're not going to be able to do predictions. But let's go ahead and figure out what this is. Well, all we have to do is plug it in. So negative 173.51 plus 4.827 times 72. It's a weird looking 2. And I get 174.05. So since these look like these are whole numbers, you probably chop that off or go up to 175. But that would be my predicted final exam score. So like I said, this stuff's fairly simple. Again, the calculator does all the work. You just got to interpret the numbers that you see. Let's do the next example. So let's go over to tests. Go to linear regression t-test. Now this time you want list 3 in X list, list 4 in Y list, and then everything should remain the same since we just did it. You just got to change your X list and Y list. You hit calculate, and there are some of your numbers. Y is equal to A plus BX. We get A is equal to 67.349. We get B is equal to 1.066. Let's see, our degrees of freedom is equal to 4. Let's see, R is 0.224. Let's see, let's put one more value up here, P value, 0.669. Alright, so now if we're still doing this at alpha is equal to 0.05, let's see, our null hypothesis is still the population correlation coefficient is equal to 0, and then our alternative hypothesis is it's not equal to 0. Comparing the p-value, 0.669, well, that's greater than my alpha value. We do not reject. And that's not surprising. We looked at the scatter plot of this, and the line, all the values were way far off the line. So that should suggest that we have no correlation. Okay? Look at our R value. It's close to 0, whereas our last R value was a lot higher. And we had a significant correlation. So all this is saying is that this line should not be used to make predictions on your range of X values. Let's look at our range of X values. The smallest amount of hours studied was 4. The largest amount of hours studied was 10. Okay? So you should not use this line to predict at all, especially within that range. You should really not go outside of that range. So maybe you need to collect more data to change the decision. Who knows? We need to see. Now, there is another way you could come up with this decision using the R value. The R value can be used as like a critical value. And if the R value, the absolute value of the R value is greater than the critical value, you reject the null hypothesis. Now, you get this critical value from a table. On that table, if you were looking at my lecture notes, you've got degrees of freedom, and then you've got critical values. They do say plus and minus version, but you don't have to worry about that if you take the absolute value of R. Now, degrees of freedom, if you recall, is n minus 2. So 1, 2, 3, 4. If you look at this, 1, 2, 3, 4, and you go over on this list, it was 0.8. It's 0.811. Our R value was 0.22. So 0.22, is that greater than 0.811? No, it is not. So if it was, we would reject the null hypothesis. Okay, so here's another way you could come up with your conclusion. Now, this table is for a 95% critical value. You could have a different table for a 99 or like a 90%, but all these examples that we're going to do are going to be a 95%. Now, that concludes the chapter. 12.5, again, if this equation is significant, if you can use it for predictions, all you have to do is plug in whatever value they want you to plug in and output the value.